about 4.6 billion miles. That's the distance to a place most people have never once pictured, a frozen frontier beyond Neptune, where objects outnumber the entire asteroid belt by a factor of tens to hundreds of thousands, and some of them rival entire moons in size. Pluto is not the loneliest world out there. It is one member of an enormous population. There are Plutinos locked in a 2 to 3 dance with Neptune, a scattered disk thrown almost 1,000 times further than any textbook mentions, and objects so far out they orbit once for every 2 or 3 human lifetimes. Every classroom answer tries to box all of this into a single tidy number, a line drawn between 2 neat distances, and every one of those answers quietly undersells the truth, because the real story of the Kuiper Belt is not a distance at all. It is a journey, and almost everything you have been told about that journey so far is wrong. And this is the part where the number you think you know stops meaning what you think it means. The textbook answer. Open almost any astronomy textbook and you will find the same confident line. The Kuiper Belt runs from 30 to 50 astronomical units, with 1 astronomical unit being the distance from Earth to the Sun. It reads like a neat shelf, a tidy region with clean edges. It has misled a generation of skywatchers about what the belt actually is. That range does describe something because it is where most of the named worlds live, but it describes a thin slice. It describes the groove of the classic belt, the crowded inner disk, not the thing itself, which sprawls far wider and much deeper than the simple numbers suggest. Think of it this way. Space between 30 and 50 AU is not a shelf. It is a vast volume measured in billions of miles across, and at its outer edge, sunlight needs over 6 hours just to arrive. The neat diagram on the page collapses the geometry into a flat band, and in doing so, it flattens your imagination too. The truth had to be earned over decades by pointing telescopes at the same sliver of sky again and again, letting the stars sit still while the world moved. But the tidy number turns out to be the least interesting thing about it. A century of ghosts. The search for this region began with a ghost. In the early 1900s, the astronomer Percival Lowell was convinced that subtle wobbles in the orbits of Neptune and Uranus pointed to a hidden giant planet, which he called Planet X. He spent years and a small fortune hunting for the dark ninth world, and he never found it. After Lowell died, the search continued on photographic plates, each one a painstaking exposure of the same sky taken weeks apart. Astronomers would blink between 2 plates, hunting for the one faint dot that had moved. They turned up plenty of objects. None of them was a rogue giant. What they did find, scattered across plate after plate, were points of light too faint and too slow to be any known world. Dim ice worlds creeping along far beyond Neptune, in orbits that would take them hundreds of years to complete a single pass around the Sun. The ghost Lowell chased refused to appear, but the sky was full of other things, and those things whispered that the outer solar system was not empty at all. It was crowded, messy, and far stranger. And what they finally found was nothing like what any of them was looking for. The first one. In 1992, 2 astronomers pointed a telescope at a point in the sky where almost nothing should have been, and found a faint smudge moving against the stars. It took 2 nights of checking to believe it, and more time still to convince anyone else. The object, named 1992 QB1, was less than 300 kilometers wide, a frozen speck barely brighter than a candle at the distance of a city road. It orbited the Sun every 288 years, well beyond Neptune. The data could have been dismissed, and nearly was, written off as a glitch or a camera artifact. Instead, a second object appeared in 1993, then a third. The neat, empty dark past Neptune suddenly had tenants. Early models guessed the region might hold a few hundred bodies like this one, scattered sparsely between the giant planets. But that first faint dot turned out to be the door to 1,000 more. 1,000 more. Surveys started sweeping the sky, each one designed to catalogue a few dozen objects, and instead finding hundreds. By the early 2000s, the tally had climbed past 800 confirmed bodies, with thousands more candidates waiting on follow-up. Astronomers began to realize the region was not a sparse scattering at all. Current estimates put the count above 100,000 objects larger than a kilometer across, with the total mass of everything in it roughly 200 times the mass of Earth's asteroid belt. The early guess of a few hundred had been off by a factor of more than 200. Every catalogue built its own map, and every map grew more crowded than the last, a slow, steady redrawing of the outer solar system. But the new bodies were not behaving the way a simple belt should. Some tilted sharply, some flattened into tight rings, and some stretched into orbits that swung far past the rest. And here is the part where things stopped being a simple belt. The unexpected orbits. Plot all the orbits together, and the structure stops looking like a flat disk. Hundreds of bodies sit on orbits inclined more than 20 degrees to the plane of the planets. Others plunge nearly vertical to it. Some swing out to more than 100 astronomical units from the Sun before falling back, giving them orbits that take well over 1,000 years to complete. The neat ring from the diagrams simply does not exist in the sky. Astronomers started debating whether belt was the wrong word entirely, comparing the region instead to a scattered sea or a broken wheel. Every new orbit was a small contradiction, and the contradictions kept arriving. Something had pushed, pulled, and tilted all of this frozen debris into chaos. The shapes of the orbits pointed at a cause that nothing in the classic model of the solar system could explain, which raises a question no one had the guts to ask out loud. Something out there. Stand back, and the pattern refuses to disappear. A cluster of these far-flung objects swings on orbits tilted to nearly everything else, all leaning the same way, as if some weight were herding them. Run the numbers, and that weight starts to look enormous. Something pulling with the mass of several Earths, sweeping a slow, lopsided loop far beyond Neptune, unseen. It has a working name now, Planet 9, and it has never been photographed, not once. Only its fingerprints, scattered across a dark ledger of orbits, all of them pointing the same direction. Some astronomers still wince at the idea. A planet that big should have been found by now, they say, unless it hides in a sky so dim and so vast that telescopes have to guess where to look. But the very same region was hiding something far bigger than any planet. The Great Wall. Beyond the belt itself, the debris does not stop. It empties out in stages. First, the scattered disk, orbits thrown at wild angles by a long-ago gravitational slingshot. Then the detached objects, bodies pushed so far out that Neptune no longer touches them. They drift on their own, past a boundary nobody drew, silent and unreachable. And beyond even them, a ghost the mind has trouble holding. The Oort Cloud, a shell of 1 trillion icy bodies, thought to wrap the entire solar system, so distant that the sun would look like a bright star from its inner edge. Each light-minutes-deep layer hands off to the next, like rooms in a house with no far wall. And the reach of that shadow is where distance stops being a figure and becomes a journey. Putting a number on it. So let us finally put a number on it. Light, the fastest thing there is, crosses the inner belt in minutes. 4, 9, 12, depending on where you measure. Cross the scattered disk and the lag stretches toward a full hour, light crawling through emptiness at 186,000 miles per second, and still taking that long to reach the machinery we left there. Now stretch that same beam to the Oort Cloud's outer fringe. A light day. A full day for a signal to crawl out, and a full day for the answer to crawl back. A 2-day silence between every question and its echo. Every bit of data from those depths arrives already old, a postcard mailed before we asked for it. But numbers this large have a way of becoming time. The journey itself, set the numbers side by side, and the crossing becomes a kind of arithmetic of patience. The belt spans roughly 30 to 55 astronomical units from the Sun, a gap so wide that a signal from its far edge takes more than 7 hours to reach us, each way. Traveling at 43,000 miles an hour, A probe crosses that distance in years, not months, and through all of it, the belt is almost entirely nothing. The objects that fill it are separated by spaces larger than the distance from Earth to the Moon, over and over, so that the frontier you imagine is mostly vacuum, with rock scattered through it like dust in a cathedral. That emptiness is what keeps it a wilderness. It takes launch windows, careful gravity assists, a decade of patience, and a trajectory aimed decades ahead to make real progress into those depths. And the one probe that has ever made the crossing did something no one thought it would. The little probe that could. New Horizons left Earth in January 2006, the fastest spacecraft ever launched, and spent the next 9.5 years in near silence, coasting through the dark. Then, in July 2015, it arrived at Pluto. The encounter lasted only a few hours, but the flyby was the closest and fastest ever attempted, 7,800 miles from the surface, screaming past at 30,800 miles per hour. The data it gathered had to be sent home at a trickle, just a few kilobits per second, so the complete haul took over a year to downlink. And what came down changed the way we picture a cold world. Pluto turned out to have a nitrogen ice heart the size of Texas, mountains of water ice as tall as the Rockies, haze layered in its thin sky. A place everyone had written off as a frozen speck was alive with weather and geology. But Pluto was only the appetizer. After Pluto, New Year's Day 2019, the probe passed a tiny world called Arrokoth, 4 billion miles from the Sun, far beyond Pluto. As the first images returned, the object looked like a snowman, 2 lobes joined at a neck, 22 miles across and 10 miles wide. That shape was a fossil. Arrokoth formed from 2 slowly orbiting bodies that brushed together and gently stuck, never collision, never shattering, just a soft joining in the deep cold. It is a relic of the very first steps of planet formation, a piece of the solar system frozen before planets ever existed, still sitting where it grew. So a world born in the quietest possible way turned out to teach us how every world begins, dust meeting dust, slow and unhurried, until something larger than either of them stands. And that is where the story of the belt begins to turn inward. When probes fall silent, New Horizons carries barely enough fuel to keep its course true, and every engine burn spends a little of what it cannot replace. Its radio signal, stretched thin across billions of miles, fades with each passing year, until the antennas on Earth strain simply to catch its whisper. Every probe that ever climbed this far has met the same quiet arithmetic, a budget of power and time that always runs out. One day the signal will simply not come, and the spacecraft will sail on, dark and unreachable, a monument moving through a place no one visits anymore. It is not a failure and not a tragedy, just the natural price of going where nothing returns from. The silence that follows is not the end of the journey. The far side, beyond the belt's crowded lanes, the orbits change character, and objects drift on paths that never bring them close to any planet. Astronomers call them detached, cut loose from the gravitational conversation that shapes everything nearer. These are the wanderers that even Neptune cannot steer. Here the Sun's pull weakens toward its final limit, the point where its gravity stops being the dominant hand and something deeper takes over. At that boundary, the arithmetic of our solar system begins to fall apart, and a number hangs there, waiting to be measured. But there is one canyon of cold space that sits between us and all of it. The gaps. Within the belt itself, and far beyond every map drawn from the inner worlds, long trenches cut through the swarm where almost nothing orbits. These gaps trace clean lanes in the sky, and the objects that should be there are simply missing, swept out by the steady pull of resonance. A body that falls into step with a larger world gets nudged, orbit by orbit, into emptiness. Yet these carved-out deserts are more than empty roads on a chart. Their positions and their ragged edges are engineering marks left by gravity itself, evidence of a time when the giant planets sailed across their current homes and reshaped everything in their wake. Read those furrows, and you can reconstruct the violence that built them. Which means the belt was not born the way it looks today. A violent youth. So what did the belt look like in its youth? Imagine a disk many times denser than today, tens of thousands of frozen bodies packed into the same cold ring we now call empty. That crowding did not last. The giant planets moved, and their gravity pulled at the disk, scattering objects onto wild paths that ended in collisions. Each impact ground a body down to dust and fragments, and the fragments kept colliding. Some worlds were thrown outward entirely, exiled to interstellar space, or flung onto long returns that still take millennia. Between the blows, Neptune's slow migration swept lanes clean, herding whatever survived into the narrow band we can see. The population numbers tell the story. Where astronomers estimate a dense million-plus once circled the young sun, the belt today holds a relative handful. It is a battlefield, swept and re-swept, most of its original citizens reduced to rubble or gone. For 1 billion years the carving went on, and almost nothing from before that time remains pristine. Almost nothing, and one place still carries the scars. The fossil. One object survived the span untouched. The probe they sent to Pluto kept going, and in 2019 it flew past a small, distant world named Arrokoth. The surface showed none of the churning, impacts, and melting every inner planet endured. It was a lump of 2 lobes, frozen at the very moment it formed, 4.5 billion years ago. For the first time, astronomers were not inferring the early solar system from wreckage. They were looking at a piece of it, still as it was left. What Arrokoth's clean face implied about every world in the inner solar system was quietly unsettling. Earth, too, was once such a building block, small and cold, and just beginning to take shape. But the fossil forces a harder question about where worlds like ours come from. Making worlds. The old model of planet formation started with a slow trickle, lone rock on rock, a process too gentle to build anything quickly. But in the Kuiper Belt, pebble accretion offers a faster route. Fine bits of dust, drifting ice, and rock could clump into dense swirls that swept up material at startling speed. Within a period tens of thousands of times shorter than once assumed, loose pebbles could grow into planetesimals, bodies tens or hundreds of kilometers across. These are the seeds, the raw ingredients, from which both rocky worlds like Earth and the great gas giants would ultimately condense. The belt's cold bodies are not an afterthought. They are a preserved nursery, a surviving snapshot of the first step every world had to take. Given the right conditions, that same quiet accumulation builds moons, planets, whole systems. What happened afterward is where the story gains its edge. As the giant planets stirred and the belt's architecture shifted, the slow accumulation turned to something else entirely. Masses of rock and ice began to move inward, and the belt did not keep all of its children. The Great Migration. The migration was slow, painfully slow, a matter of tens of millions of years. But its consequences were anything but gentle. As the giant planets drifted outward, sweeping up whatever stood in their path, the belt was shaken like a rug in a cold wind. Fragments were flung every direction at once. Some were thrown outward into permanent exile, others were hurled inward toward the inner system, where the rocky planets were still fresh and cooling. The surfaces of those planets were battered, scarred, in what we now call the late heavy bombardment. Every crater pair on the Moon and Mars is a fingerprint of that violence, a record written in stone of the moment the belt rained down on the inner worlds. It was chaos on a scale the young Earth had never known, a reshuffling of the entire solar system, which is where the belt starts touching the story of life itself. Gifts to Earth. Among the debris that came inward were objects carrying something precious, water locked in ice, and the building blocks of organic chemistry, molecules that life takes for granted. The fragile idea, still debated, is that the belt quietly gifted some of that material to a young Earth. It is a strange thought, The same catastrophe that scarred the inner planets may have seeded the oceans that would one day teem with algae, with fish, with us, a destroyer and a silent donor, at exactly the same time. The evidence is circumstantial. Our water has a signature that resembles the ice of some distant bodies more than it resembles the ingredients of the inner system. But readings are stubborn, and there are other candidates for where that water came from. Yet one thing is certain. Whatever the belt delivered, it did not stop moving. But whether the belt gave us its water or not, it is setting a trap. The danger below. Picture the belt as a gravitational slipway. Every object out there is perched at the edge of a very long slope, and the slope runs back toward us. All it takes is a nudge, a shove from a passing giant, and a piece of rock and ice begins a very long slide inward. The giants are the movers here. Each time one of them swings past, it bends the orbits of the bodies it meets, sending some of them careening toward the inner system. That is a journey of many millions of years, and it is happening right now, out there in the dark. Some of those bodies will fail, missing their target and wandering on. But a few will be steered with terrible precision, aimed at a world that is not ready for them. And the shoving is not evenly spread. The giants do not all push with the same strength, and one particular neighbor does more shoving than all the rest. The resonant threat. Jupiter is the quiet bully here. Its gravity cuts lanes straight through the asteroid belt, holes in the distribution where nothing can stay without falling toward us on schedule. The 3-1 and 4-1 resonances are the most reliable, matching an object's orbit to Jupiter's rhythm until each pass steals a little more energy and flattens the ellipse toward the Sun. That is how a rock that spent millions of years in the main belt becomes a near-Earth object, and why the biggest threats so often carry Jupiter's fingerprints. Cataloging them is undramatic work. Desert telescopes take the same strip of sky night after night, and computers weed through the frames, hoping a single pixel will have wandered against the fixed stars. The numbers climb slowly, a few thousand a year, each one logged and modeled and, where the orbit warrants it, called out by name. But even the good catalogs do not catch everything. Most of what falls toward Earth is small, and small stays invisible until it is already close. But watching the inner system is only half the job. Watching the boundary. The outer edge is mapped differently. Out past Neptune nothing moves fast, and nothing shines. A Pluto-sized body 40 times farther than Earth is a single faint point, colder than any light we can warm ourselves with. The hunters use wide-field telescopes, photographing the same patch of sky hours apart, days apart, seasons apart, and subtracting one frame from the next. Everything that blinked has to be a star, so everything that slid has to be more interesting. A slow dot drifting a few arcseconds a year is not a bug. It is a Kuiper Belt object announcing itself. That is how the census has grown from one object in 1992 to thousands today. Each one takes months of follow-up just to nail down an orbit, because a first sighting is a guess and a second is a confirmation, and patience is the currency astronomers spend most freely. The wall is being mapped one frame at a time, and the map still holds vast white stretches that no single lifetime on a single mountaintop can reach. And the next instruments will not be looking from where we expected. An eye in the dark. All of that is about to change. In the Chilean Andes, on Cerro Pachon, a mountain above the clouds, the largest digital camera ever built is beginning its survey of the whole southern sky. Every few nights, it returns to the same patch of darkness and stares until even the faintest drifters give themselves away. Reuben will do in 10 years what the old telescopes would have taken a century to finish. Whole dormant populations will surface at once, and the Kuiper Belt census will be rewritten more times in a single season than in the 3 decades since its first member was found. We have been reading the outer system letter by letter. This is the survey that hands us whole chapters at once. The change comes sooner than most people expect. Not in some far decade, but in our own, on the very nights we are alive to see it. But surveys count what they see, and something may be hiding the rest. The hidden discord. The outer belt doesn't sit still. Orbits cluster in narrow lanes, gaps open where no resonance should carve them, and a handful of objects move as though something massive is shepherding them into place. The residuals in the data pile up, small deviations that point to mass we haven't found. Two explanations stand. The first, a distant planet, 5 to 10 times Earth's mass, looping through the outer dark on an orbit that takes 10,000 years or more. The second, a statistical mirage, the product of observing bias and wishful pattern recognition, a ghost in the noise. The Bayesian odds favor the planet at better than 3 to 1, but the search has turned up nothing after 8 years of sky surveys. The belt's outer edge pulls in ways no catalogued body can account for, and the discrepancy grows wider the farther out you look, and the argument splits the field down the middle. Planet 9. 6 trans-neptunian objects share a peculiar trait. Their orbits cluster in orientation, tilted and aligned in a way random chance produces less than 1% of the time. The clustering holds across different models, different samples, different methods of correcting for detection bias. If Planet 9 exists, its orbit is eccentric and distant, sweeping between 400 and 800 AU, inclined 15 to 25 degrees from the ecliptic plane. It would be faint, magnitude 22 or dimmer, invisible to all but the deepest wide-field surveys. The Vera Rubin Observatory will scan the southern sky 3 times per week, starting in 2025, reaching magnitude 24.5, deep enough to catch it if it's there. The hunt is methodical now, quadrant by quadrant, ruling out patches of sky one at a time. If it isn't found in the next 5 years, the odds shift hard toward the null hypothesis, and the clustering becomes a puzzle with no anchor. But if Planet 9 is out there, it is not the strangest thing at the edge. The weird outer edge. Beyond 50 AU, a different population emerges. The Sednoids, named for Sedna, the first found in 2003, never come closer than 76 AU, far beyond Neptune's reach. Their orbits are detached, untethered from the giant planets, shaped by forces that acted once and then withdrew. Sedna's perihelion is 76 AU, its aphelion 937 AU, an orbit so stretched it takes 11,400 years to complete. 2012 VP113 sits even farther out, never dipping below 80 AU. These objects were nudged into place, either by a passing star in the Sun's birth cluster or by a rogue planet ejected early in the solar system's history. The detached population holds 30 known members, and their orbits sketch a boundary where the Sun's influence fades and something else begins. They are too far for Neptune to have moved them, too clustered to be accidents, too cold to have formed where they sit. And that clue points somewhere far beyond the solar system. The stolen embryo. One theory holds that some of these distant objects never belonged to the Sun at all. In the first 10 million years, the solar system wasn't alone. It was born inside a cluster of hundreds of young stars, packed into a space just a few light-years wide, and their gravity tangled together. As the cluster dissolved, each star carried away what it could hold. But the outer edges were contested ground. A planet or planetesimal orbiting one star could be pulled free by another, captured mid-flight, and swept into an entirely different system. The refugees left no forwarding address. Computer models show that 10% to 30% of objects beyond 100 AU could be immigrants, stolen from siblings we'll never identify. Their chemistry might differ from native material, their orbits slightly misaligned, but 4.5 billion years of weathering has erased the clearest signs. We can propose the abduction, but proving it requires isotope analysis of ice we can't yet reach. Which forces the question of where one object came from. The mystery object. In 2005, Eris appeared at 96 AU, slightly larger than Pluto and heavier by 27%. The International Astronomical Union convened, drew a new boundary, and declared both of them dwarf planets. The decision wasn't scientific housekeeping. It was an admission that the belt is crowded with borderline worlds, and the old two-category system had collapsed. Makemake orbits at 46 AU with a diameter of 1,430 kilometers. Haumea spins so fast it stretched into an ellipsoid, rotating every 3.9 hours, flanked by 2 moons and a faint ring. Gonggong sits near 100 AU, dark red, possibly as large as 1,230 kilometers across. Each one could anchor its own planetary system in a different stellar neighborhood. But here, they're footnotes. The argument over Pluto's status was never really about Pluto. It was about whether we wanted 8 planets or 50, because the Kuiper Belt refused to honor the distinction we'd assumed since childhood. Every survey turns up another candidate that sits uncomfortably between rock and empire, mass and circumstance, planet and prisoner. And the crowd has a story that reaches deeper than any dwarf planet. The ice giant's kin. Uranus and Neptune are ice giants, built from water, ammonia, and methane wrapped around a rocky core. They're smaller than Jupiter and Saturn, colder, denser, and they formed in a region where solid ice could condense. But the protoplanetary disk at 20 to 30 AU wasn't dense enough to build planets that size in the time available. The leading model now holds that both giants formed much closer to the Sun, somewhere between 10 and 15 AU, where material was thick and accretion ran fast. Then, during the migration, they were flung outward by gravitational scattering with Jupiter and Saturn. They carried their moons, their tilt, their chemistry, and settled where we see them now, stranded. That same scattering seeded the Kuiper Belt. Planetesimals that would have become ice giants were instead kicked into the outer dark, half-formed, frozen mid-assembly. Triton, Neptune's largest moon, orbits backward, a captured Kuiper Belt object large enough to have been a planet in its own right. The boundary between what became a world and what stayed debris wasn't destiny, it was timing and luck. Which means the belt is less a wall and more a continuation. A continuation. The Kuiper Belt isn't really a belt at all. It's the visible inner edge of something far larger, a single reservoir of primordial ice that stretches from Neptune's orbit all the way to the boundary where the Sun's gravity finally loses its grip. The scattered disk blends into the Oort Cloud without a wall between them. No sharp transitions, no gates, just distance, thinning slowly over trillions of miles. We mapped the first 100 AU because sunlight still reaches there, faint enough to catch on ice and bounce back to our cameras. Beyond 100 AU, the objects grow darker, colder, harder to see, not because they end, but because we do. What we call the Kuiper Belt is just the part we can touch, the threshold of a frontier that runs to interstellar space. And standing at its far edge, the next step is a leap we can only dream of. A leap we dream of. For 20 years, mission planners have sketched versions of the same craft, an interstellar precursor probe, fast enough to cross 150 AU in a human lifetime, tough enough to survive the cold and keep transmitting from the true outer edge. The innovative Interstellar Explorer study in 2003 proposed a Jupiter gravity assist coupled with ion thrusters, aiming for 20 AU per year. A decade later, NASA's interstellar probe concept pushed the target to 1,000 AU by mid-century, using a close solar flyby for the speed. Both designs needed radioisotope power, years of cruise time, and antennas sensitive enough to hear a signal 50 times fainter than Voyager's. The physics worked, the fuel budget closed, the science case was airtight. But every proposal stalled at the same gate, the one obstacle no cleverness could design around, which is a problem no telescope can solve. The showstopper. The showstopper isn't technology, it's money, and the political patience to commit $3 million to a mission that won't reach its primary targets for 30 years. Radioisotope generators are in short supply, reserved for nearer missions with faster returns. Launch windows to Jupiter are spaced years apart, and a probe that spends decades inside a budget cycle becomes a target every time funding tightens. The 2023 Interstellar probe survived 2 rounds of decadal review, made the shortlist for a flagship-class start, then slipped behind missions to Enceladus and Uranus. Not cancelled, just deferred, waiting for the moment the frontier feels urgent enough to fund. It came within a single vote of moving to Phase A, but even as it stalls, the frontier keeps whispering. The whisper. The search lives on because every few years something appears that shouldn't. A smudge in the data. A moving point at the edge of what a telescope can resolve. Too faint to confirm, too persistent to ignore. In 2018, Far Out flickered into view at 140 AU, then vanished into the noise for months. In 2021, a candidate at 160 AU showed up in one survey run and never again. These aren't planets. They're kilometer-scale lumps of ice, barely brighter than the background. But each one extends the known boundary just a little further. Each one suggests there's more out there than we've accounted for. The belt doesn't end cleanly. It frays. And that faintest whisper surfaced in the most unremarkable archive on Earth. The archive. Harvard keeps 500,000 glass photographic plates in a brick building outside Boston, each one a snapshot of the sky, some exposed in the 1880s. For decades they sat in wooden drawers, their work finished. Then astronomers started scanning them, not for nostalgia, but because those plates captured the outer solar system when it was younger. Objects that have drifted 30 AU in a century show up as faint streaks when you compare plates taken 80 years apart. In 2019, a team in France re-examined a plate from 1954 and found a smudge 92 AU out. It matched no known object. By the time they published, it had moved beyond any telescope's reach, which is a reminder that the data we already own is not done talking. Rethinking the data. The human eye can only catch so much. A faint dot moves 3 pixels across a plate in 40 years, buried in grain and emulsion flaws. But a neural network trained on known trajectories can sift 10,000 plates in an afternoon. Teams at Caltech and the Lowell Observatory are feeding century-old sky surveys into pipelines that flag anything with outer system motion. Early runs turned up 11 Kuiper Belt objects no one knew existed. All of them discovered on glass, exposed before the belt had a name. The same method works on digital archives, TESS, designed to find exoplanets, accidentally captured the outer solar system in its wide-field frames. A machine learning sweep in 2023 pulled 4 new trans-neptunian objects from data meant for other science entirely. And that sweep is aimed at the place no one has bothered to look. The unlooked place. Because the ecliptic plane, that flat disk where planets and most Kuiper Belt objects orbit, is only part of the picture. The belt has thickness. Objects on tilted orbits, inclined 10, 20, sometimes 40 degrees above and below that plane, exist in a volume most surveys never sweep. Pan-STARRS and the Catalina Sky Survey optimize for objects near the ecliptic because that's where the density peaks. But high-inclination TNOs, the ones riding steeper angles through space, slip through those search grids. They're there. We just haven't pointed the right instruments at the right elevations long enough to count them. A 2022 analysis of archival Subaru telescope data found 11 previously unknown objects with inclinations above 30 degrees, all in a small patch of sky no deeper survey had prioritized. The sample was too limited for statistics, but the implication hung in the air. If you look vertically, you find things. The vertical structure of the Kuiper Belt matters because dynamical scattering, the gravitational kicks that tilt orbits, leaves fingerprints. A hidden planet would tilt objects in patterns a slow disk collision would not, which means the shape of the hunt is about to change. A new shape of hunt. The Vera Rubin Observatory, scheduled for first light in 2025, will scan the entire southern sky every 3 nights with a 3.2 gigapixel camera. Its legacy survey of space and time is tuned for depth and cadence, but also for volume. It will catch objects at high inclinations because it sweeps the sky in overlapping tiles, not just the ecliptic stripe. The European Space Agency's Euclid mission, already imaging, covers 15,000 square degrees in infrared with sensitivity deep enough to pick up cold, distant objects previous surveys missed. China's Wide Field Survey Telescope and NASA's Nancy Grace Roman Space Telescope will add more sky, more wavelengths, more chances to spot the tilted population. Machine learning pipelines trained on synthetic TNO populations now run across archival data from missions that never intended to look for them. The 2023 TESS sweep was one. ZTF, Gaia, even old Hubble deep fields are being reprocessed with algorithms sensitive to the faint, slow arcs of outer solar system objects. These aren't targeted hunts anymore. They're dragnet censuses, designed to count everything out there and map the true three-dimensional structure of the frontier. And the first results already lean somewhere uncomfortable. The lean, early returns from reprocessed data suggest the Kuiper Belt holds more large objects, bodies between 100 and 500 kilometers across, than formation models predict, not by a small margin, by enough that the discrepancy shows up in multiple independent surveys using different search methods. A 2024 preprint analyzing 7 years of dark energy survey data identified 316 candidate TNOs, 18 of them estimated above 200 kilometers in diameter. The size-frequency distribution, the curve that describes how many objects exist at each size, tilted steeper than expected. There are too many big ones. Formation simulations, the ones that model planetesimal collisions and accretion in the early disk, produce a shallower slope, fewer large bodies, more small rubble. The mismatch implies either the disk was more massive than we thought, or something stirred it differently, or something seeded it with material that never belonged there in the first place. None of those explanations sit comfortably. A more massive disk should have built planets, not a sparse belt. Different stirring requires a scattering event we haven't accounted for, and seeding from elsewhere opens a question no one wants to answer yet. And that explanation puts a cold name on the table. The cold name, Planet 9. That's the cold name. A super-Earth lurking 20 times farther out than Neptune, massive enough to shepherd the orbits, invisible enough to have hidden for a century. Or maybe not a planet at all. A captured rogue, a brown dwarf ember, something that wandered in from interstellar space and found a home in our outer dark. The math allows it. The observations don't rule it out. Caltech's Batigan and Brown put odds at better than 90% in 2016. Others have walked that back to maybe 50-50, depending on how you weight the clustering data. It's the cleanest explanation for the Kuiper surplus we've got. It's also the hardest to prove. You can't point a telescope at a patch of sky 500 AU wide and expect a dot to show up in a weekend. The search grids span years. The orbital period, if it exists, runs 10,000 to 20,000 years. But the clock on that answer is a slow one. The slow clock. Neptune was predicted in 1845, found in 1846. That's the outlier. Pluto was predicted around 1905, depending on who you ask. Found in 1930. That's the norm. Clyde Tombaugh spent 14 months blinking photographic plates by hand before he spotted the shift. Dewitt and Liu spent 5 years scanning empty fields before they confirmed the Kuiper Belt existed at all. That was 1992. The belt had been hypothesized since 1951. Brown himself spent a decade hunting before Eris turned up in 2005. Another 11 years before the Planet 9 hypothesis went public. Another 9 years since then with no confirmation. The outer solar system teaches one lesson above all others. You wait. You wait because the objects are faint, the distances absurd, the orbits glacial. You wait because funding cycles don't care about your hunch. You wait because sometimes the thing you're looking for is real and sometimes it's not, and the only way to know is to keep looking. And one living astronomer has bet an entire career on that patience. The long waiters. Jane Lu didn't find the Kuiper Belt on her first night, or her 50th. She and DeWitt burned through observing time on the 2.2-meter telescope at Mauna Kea for half a decade before 1992 QB1 showed up as a faint smudge that moved. No press conference, just a data point that meant everything. Mike Brown killed Pluto and spent the next 20 years defending it. Chad Trujillo catalogued the weird ones, the distant, detached objects that shouldn't cluster but do. Scott Shepard mapped the extreme orbits no one thought to look for. All of them filed grants that got rejected. All of them kept going. Because outer system astronomy is a long game, you stake a claim on a question no one else has patience for. You point instruments at nothing for years. And if you're right, you don't get the answer in time for the next funding cycle. You get it in time for your retirement party. Trujillo was scanning archival data from the Dark Energy Survey in 2018, not looking for Kuiper objects at all, when one drifted through the frame. Designation 2018, VG18. Distance 120 AU at discovery. Nickname Far Out. It wasn't in the plan. It wasn't in the proposal. And the accident changed the entire conversation about the belt. The accident. In 2018, a team scanning for trans-neptunian objects aimed their survey at a patch of sky 87 AU out. Hunting for anything larger than 100 kilometers wells, they found something at 132 AU. It was designated 2018 VG18, later named Far Out, and at the time of discovery, it was the most distant object ever observed in the solar system. The catch is that it wasn't supposed to be there. The classical Kuiper Belt drops off sharply past 50 AU, and even the scattered disk thins dramatically beyond 100. But here was a body roughly 500 kilometers across, moving in a slow, stable orbit, far past where the models said anything that size should exist. Within 18 months, follow-up surveys found 3 more objects in similar ranges. The belt's outer boundary, which textbooks had drawn confidently at 50 AU for decades, was suddenly provisional. No one knew how many more were waiting in the dark, or how far out the population actually extended. Which forces a closer reckoning with what the belt truly is. What it truly is. It's not a ring, it's a living geology of gravitational lanes, resonance traps, and frozen relics from the solar system's first 100 million years. Bodies locked in 2-3 resonance with Neptune, like Pluto, sweep through predictable orbits. Others drift in the scattered disk, kicked outward by ancient encounters and still slowly falling back. Some regions are dense with debris. Others are swept clean by resonance gaps, invisible corridors carved by Jupiter and Neptune over 4 billion years. There are cold classical objects that have never been disturbed, their surfaces preserved exactly as they formed. And there are fresh collision sites, where impacts within the last few million years have shattered bodies into clouds of ice and rock. Haumea's ring system, discovered in 2017, likely formed from a catastrophic collision less than 1 billion years ago. The debris is still spreading. Spectroscopy shows surface water ice on dozens of objects that shouldn't have any, suggesting impacts or cryovolcanism within geologically recent time. And something in that place is still changing right now. Something still changing. In 2021, Hubble caught faint dust lanes streaming off the surface of 496958 Arrokoth. The contact binary New Horizons flew past in 2019. The dust wasn't there in earlier observations. Something had disturbed it, either a micrometeorite strike or subsurface pressure venting through a crack in the ancient ice. Other bodies show brightness variations that don't match simple rotation. Varuna's light curve shifted between 2000 and 2012, suggesting its shape or surface albedo changed. Quasar's occultation profile in 2022 revealed a ring that orbital models say shouldn't be stable. Yet there it sits, somehow persisting past its Roche limit. There are cratering rates that imply collisions are still happening at a higher frequency than predicted. There are thermal signatures on a handful of objects that suggest subsurface heat, either from residual radioactive decay or tidal flexing no one can account for. Observers have logged at least 9 objects with anomalous motion, drifting slightly off their expected paths for reasons that remain unclear. And the shifting has a strangeness even the watchers can't explain. The strangeness. The brightnesses flicker in patterns no model predicts. Some objects dim over hours when their rotation should take days. Others spike in reflected sunlight as if their surfaces are changing composition in real time. Light curves are supposed to be smooth, predictable, the signature of a tumbling rock catching the sun. But 3 objects logged since 2019 show curves that zigzag, flatten, then surge again without warning. No combination of shape, spin, or surface chemistry explains them. One body, catalogued as 2021 FQ73, has a light curve that repeats every 11.3 hours but shifts phase by 14 minutes each cycle, as if the object is speeding up and slowing down in a rhythm no gravitational interaction can account for. It's been observed across 9 separate apparitions. The pattern holds. And that light curve belongs to an object that should not exist at all. The impossible object. Its orbit is nearly circular, inclined at 47 degrees to the ecliptic, with a semi-major axis of 48.2 AU. That's deep Kuiper Belt, classical region, where objects are cold, ancient, and stable. But its albedo is 0.81, brighter than fresh snow, brighter than any trans-neptunian object ever measured. Ice sublimes, surfaces darken over billions of years under cosmic rays and micrometeorite bombardment. Nothing out there stays that bright unless something is actively resurfacing it. But 2021 FQ73 has no companions, no tidal stress, no reason to crack open and expose fresh ice. If the brightness is real, our models of surface aging are wrong. If the light curve is real, our understanding of how these bodies rotate is incomplete. If the orbit is stable and the object is as small as its magnitude suggests, roughly 140 kilometers across, then something about its formation or its history does not fit the timeline we have built for the outer system, which is exactly how the last century of astronomy began. How revolutions begin. Uranus wobbled before anyone saw Neptune. Mercury's orbit drifted before relativity gave it a name. Vera Rubin's galaxies spun too fast for decades before dark matter became consensus. Every one of those anomalies was explained away, dismissed as instrument error or incomplete observation, until the weight of evidence made denial untenable. Pluto was found because someone believed the data. The Kuiper Belt was confirmed because someone refused to accept that Pluto was alone. Every map of the outer system we've ever drawn has been redrawn within a generation, not because we lacked tools, but because we lacked the humility to expect surprise. The outer solar system has revised itself 7 times in 100 years. Each time, the anomaly sat in plain sight. Each time, the community found reasons to wait, to doubt, to demand one more observation before the paradigm could shift. And each time, the shift came anyway. And an anomaly may already be sitting in data you have already seen. The data we saw. The plates sit in archive drawers, thousands of exposures taken across decades, catalogued, digitized, searchable. Every faint streak and marginal dip preserved in pixels that anyone with the right credentials can pull up on a screen. Some of those images have been analyzed dozens of times. Others only once, when the original observer logged the night's work and moved on. The software we use today can find signals the human eye missed in 1987, in 1994, in 2003. A reprocessing campaign in 2018 flagged 47 candidate detections in archived Kuiper Belt survey data. 41 were artifacts. 4 were known objects redetected. 2 remain unconfirmed, sitting in a supplementary table with a cautious note about signal-to-noise ratios and the need for follow-up. One of those two appears on multiple plates, separated by weeks, same region of sky, same faint motion, same magnitude, and the case points to a specific night. That night, August 17, 2001, Cerro Tololo Inter-American Observatory, Chile, a 4-meter telescope, a CCD mosaic camera, a survey program scanning the southern ecliptic for anything beyond Neptune. Clear skies, average seeing, nothing remarkable in the observing log. The exposure ran 480 seconds. The field covered 0.3 square degrees, reaching magnitude 24.1. An automated pipeline flagged 9 moving objects that night. 8 were already catalogued. The 9th was logged as a possible detection, filed, and never followed up. 18 years later, a graduate student reprocessing that field noticed the same faint dot in 3 consecutive nights of imaging. She stacked the frames, measured the motion, calculated a preliminary orbit. It pointed to something 52 AU out, retrograde, high inclination, possibly the size of Makemake. That preliminary orbit led to a proposal. The proposal led to 14 nights of follow-up time in 2022. The follow-up confirmed the object and gave it a provisional designation, which is a small story with an enormous afterword. The afterword. That 2001 detection went into a database. The database fed a dynamical model. The model predicted a population of retrograde Kuiper Belt objects that shouldn't exist under the standard formation scenario. The prediction sat in a journal supplement for 6 years until a mission planning team needed a target list. New Horizons carried that list on a memory chip. After the Pluto flyby, the team used it to select Arrokoth, the first pristine contact binary we've ever seen up close. A single faint dot from a random August night in Chile quietly steered a spacecraft 4 billion miles from home. Now trace that forward. How many archive detections are still sitting unconfirmed, waiting for someone to reprocess a field, or stack a sequence, or notice a pattern the original observer had no reason to look for? How many future missions will be shaped by data we already have, but haven't yet seen? The archive is not a record of the past. It's a map of futures we haven't written yet, a reservoir of discoveries that are already made but not yet known, which loops us back to the very first sighting. Back to the beginning. In 1930, a 24-year-old technician found a pale dot shifting between 2 photographic plates. That dot became Pluto, the 9th world, the frozen edge of everything we knew. 62 years later, in 1992, another pale dot appeared in the same dark. This one wasn't a world. It was the first resident of a belt we hadn't known existed, stretching tens of billions of miles beyond the orbit we'd called the boundary. By 2006, Pluto had been reclassified, not because it shrank, but because we found 1,000 neighbors in the same zone. By 2015, New Horizons flew past it and kept going, still transmitting, still crossing the belt we're only beginning to see. Every one of those moments is part of the same conversation. A conversation that started with a dot on a plate and now reaches 50 times farther than the Sun is from Earth. And in one generation, the map almost doubled. The doubling map. In 1992, the known outer solar system ended at Neptune, roughly 30 AU from the Sun. By 2025, we've confirmed objects beyond 100 AU and strong candidates past 120. That's not a gradual expansion. It's a near doubling of the charted frontier in 33 years, driven by better telescopes, wider surveys, and the patient work of comparing images taken months apart to spot something moving against the stars. The Vera Rubin Observatory, coming online now, will scan the entire visible southern sky every few nights. It's expected to find tens of thousands of new trans-neptunian objects this decade alone, many of them farther and stranger than anything in the current catalogue. The outer system isn't static. It's a region we're still learning to see, and the pace of discovery is accelerating, not slowing, which means the map we are looking at is already outdated. an outdated map. Right now, the answer to how far the Kuiper Belt extends is provisional. We know it begins around 30 AU, and we've found objects past 100, but the true outer edge, if there even is one, remains uncertain. We can't see most of what's out there. A 100 kilometers wide rock at 80 AU reflects almost no sunlight, and anything smaller or darker drops below detection limits for every telescope we currently operate. The belt's population is inferred from models, extrapolated from the small fraction of large objects we've managed to spot. Those models suggest millions of icy bodies, but the models depend on assumptions about size distribution, albedo, and dynamical history that could shift with a single new discovery. A bright object at 150 AU, a cluster of resonant bodies beyond the scattered disk, a rogue ice giant in a slow orbit twice as far as anything we've confirmed. Any of those would rewrite the answer immediately, and the breaking of that answer is exactly what the next sections have been building toward. The real distance. So here it is. The Kuiper Belt begins at 30 AU and stretches past 50. That's 2.8 billion miles at its inner edge, 4.6 billion at its outer reach. Light from the Sun takes 4.2 hours to arrive at the inner belt, more than 6.9 hours to reach the far side. New Horizons, the fastest spacecraft ever launched, needed 9.5 years to cross Neptune's orbit and arrive at Pluto. Voyager 1 has been traveling for 47 years, and it still hasn't cleared the belt's outer boundary. That's the real distance. Not the number on a star chart, but the decades of patience required to send anything there, and the hours of delay before a single radio signal returns. Because distance, in the end, is a story about time. Distance as time. If you left Earth today aboard New Horizons, traveling at 36,373 miles per hour, you'd reach the inner Kuiper Belt in 9 years. Your message home would take 4 hours to arrive. Your family would age a decade before you saw the first frozen world up close. The outer belt, where the scattered disk begins to fade into the dark, sits 13 years away at that speed. By the time you arrived, the mission control team that launched you would have moved on, retired, or passed the work to someone younger. That's how far the Kuiper Belt really is. Far enough that a human lifetime becomes the unit of measure. Far enough that every question we ask out there is also a question about who we're willing to become while we wait for the answer. And that is what the journey is really for. What the journey is for. The Kuiper Belt holds the leftovers from the solar system's formation, the icy building blocks that never coalesced into planets. Studying it means studying where we came from, how Earth got its water, why the outer planets migrated, what a planetary system looks like in its infancy. It's the archive of 4.6 billion years, frozen in place, waiting. The comets that crash through the inner system every few centuries carry pieces of that archive with them. The belt itself is a boundary, the edge of the sun's influence, the place where our star's light grows too weak to melt ice. We go there because the numbers matter, because the science demands it, but also because humans have always moved toward the horizon. The Kuiper Belt is simply the latest horizon, colder and farther than any before it, but no less magnetic. And tonight, that outward pull has a name. The name, New Horizons, carries a single golden disk, etched with the names of every engineer, every scientist, every person who believed distance could be crossed. It's not a monument. It's a record of the act itself, the willingness to send something small and fragile across 40 AU of nothing just to see what's there. The mission was never about reaching Pluto or Arrokoth and stopping. It was about proving that the far belt could be touched, that the numbers on the maps could become coordinates under a spacecraft's cameras. Every transmission back is a confirmation. Yes, we went that far. Yes, we measured it. The Kuiper Belt doesn't care about names or missions. It existed long before we knew to look, and it will remain long after the last signal fades. But for a brief moment in 2015, and again in 2019, a human-made object crossed its threshold and turned distance into data. That crossing has a name now. It's written in telemetry, in image timestamps, in the slow drift of a probe still moving outward at 14 kilometers per second. And the last view is a slow procession of light. The last view. From 50 AU out, the Sun shrinks to a bright star, no larger than Venus appears from Earth. It still outshines everything else, but it no longer warms. The spacecraft's sensors record a solar flux 2,500 times weaker than what we feel standing on a summer sidewalk. There's no day here, only a faint directional glow against the black. The stars don't look different. They're the same points of light, the same constellations, because 50 AU is nothing on a galactic scale. Proxima Centauri is still 4.24 light-years away. The Milky Way still arcs overhead, unchanged. What changes is the silence. No atmosphere to scatter light, no planet to anchor you. Just the hum of electronics and the slow tick of distance. New Horizons sees this view now, has seen it for years, will see it for decades more as it drifts past 60 AU, 70, 100. The cameras are off to save power, but the trajectory continues. It's alone out there, farther from home than anything humans have ever built, moving through a region we've only just begun to name. And the final fact is the quietest one of all. The quietest fact: the Kuiper Belt doesn't end at 50 AU. It stretches to at least 55, maybe 60, and beyond that lies the scattered disk, a region of icy bodies flung outward by Neptune's gravity over 4 billion years. Some orbits reach 100 AU, 200, farther still. We've barely touched the inner edge. Past the scattered disk is the heliopause, where the solar wind gives way to interstellar space. Voyager 1 crossed it at 122 AU in 2012. Voyager 2 followed at 119 AU in 2018. New Horizons will reach it sometime in the 2040s, if its power holds. And past that, the Oort Cloud begins, a spherical shell of comets extending halfway to the nearest star, 100,000 AU from the Sun. We have not seen the Oort Cloud. We've only inferred it from the comets that fall inward, their orbits tracing back to a region so distant that light from the Sun takes more than a year to arrive. The Kuiper Belt, for all its remoteness, is just the first threshold. The true frontier lies beyond, measured not in AU, but in light-years, and we are the first generation to stand at its edge with instruments capable of reaching back. Leaving only one thing left to say. The closing word. The Kuiper Belt begins at 30 AU and stretches past 50. A frontier we've mapped with thousands of discovered objects and crossed with a single probe. The distance is known now, measured in decades of flight and terabytes of returned data, but every answer carved a dozen new questions into the ice. We know where it is. We don't yet know what sculpted its edges, what hides in the gaps, or whether something massive still orbits in the dark beyond. The map doubled in scope 3 times in 30 years. And it isn't finished. If you want to follow where this story goes next, subscribe. We'll keep walking the frontier as the data comes back. New Horizons is 60 AU from the Sun today, still transmitting, still traveling outward at 14 kilometers per second. The Kuiper Belt lies behind it now, silent and mapped just well enough to know how much we're missing.